I start recording and officially welcome everybody here. Hi, Zoomers. We're talking about homework, in case you couldn't tell. So lots of questions over email as well about saturating the model. So the relevant questions then for this would be 22, 3, and 4 in section 2. So at this point, you would have built up your fixed effects side of your model to have linear change during the first phase, the second phase, and the third phase, and then additionally to that, quadratic change in the first phase and the third phase. So if we count up the number of parameters that we have here, all right, we have an intercept. We'll call this lin1, quad 1. We'll go lin2 for the second phase. There's no quad 2 because there's only 2 points connecting them. We'll go lin3 and quad 3. All right. So then how many parameters do we have?
In the model for the means?
Yep. 6 things here. How many means are we trying to recreate?
No.
13, yeah. This is the audience participation portion of the program. So here's 13 means. There are currently 6 fixed effects trying to recreate them. How much room do I have to be wrong? 7. And I feel like I can give that one away because I'm pretty sure that if you worked hard enough, you could enter enough numbers until 22 turns green. And in fact, I've heard folks doing that. No, I know people do this, okay? I don't think that I don't know this. But the thing about students is that there's no matter what system you have in place to try to protect the integrity of your work, like there's always ways to work around the system. I know this. I accept it. The next question then, so we know we need 7 contrasts. Now, where do they go? Let's think about it this way. We've got 1 to 7 in our first phase. How many of these terms relate to predicting means or changes thereof from 1 to 7? I count that many. So how much room do I have to be wrong in the first section?
4 to do something?
I've got 7 means and I've got 3 fixed effects. I got room to 4. So we know we need 7 in total, right? So 3 of them would need to be, or 4 of them, I just said, would need to be in the first one. What about the second phase? Do we have room to be wrong here? Not really. So none within the second phase. Now in the third phase, from 8 on, we have 5, essentially, picking up where that one left off. So then we have 2. That leaves us with 3. So beyond this constraint, it doesn't matter which occasions you pick, but they have to be within the sections that have room to be wrong. Otherwise, there's redundancy in what the fixed effects are saying, and it won't work. I did warn you that this was the hardest homework, right? I did warn you. So it's all downhill from here. The last one isn't due until December 19th, over a month from now. It doesn't even exist yet as far as you're concerned. But this one will be, the high point. And I think quite possibly a personal best in terms of number of questions. Yeah, we're up to question 95. Yeah. Believe it or not, I actually cut it down relative to previous years when it was over 100, and I thought, okay, this is a bit much even for me. But I just want to make sure you're all challenged, okay? It's difficult to challenge smart, educated, motivated people, but I'm going to do my best. All right, what else can I talk about with respect to this? Anything else on your list, Vladimir?
Not really.
Okay.
The other things were about code, but most of the time code is just about dots or words. So those are things that we can change.
Okay.
Like, yeah.
All right. Well then, if anything else is confusing or you get stuck and you have 15 minutes of effort into one question and you're still stuck, please let us know. Please let us help you. All right. Then I'll shut this down. So yeah, just homework due next, and then I think a couple formative assessments after break, and we're almost there. Can you believe it? You're like, no, it doesn't feel that way. Well, that's the thing about the workload for each of us, is that mine is front loaded. So to me, it's like, I only have one more example to make, and I'm almost done. And you're like, yeah, no, I have 5 weeks of classes to get through. But anywho, we get to talk about predictors. Are we excited about that? Yeah, by the way, Candy Bowl, last chance. And if any of you decide that you like licorice all of a sudden, please take some. Oh, and by the way, I'm wearing pink today, just to prove that I do own other colors. I was tempted to take a picture of my closet and be like, look, it's just that I only wear 4 shirts. But the other ones are all still there, just in case, someday I decide to shrink or grow or, otherwise fit back into them. Anywho, the slides are yellow. My shirt is pink. A lot of you are wearing black or gray. So we all have our choices, right? It's all good. So the reason I picked yellow for this, by the way, is because I knew I would be having red things and blue things, and I needed a background that wouldn't conflict with that. And the SEM class, by the way, is purple, because in that class there are actually fixed effects in the model for the variance. And so the red and blue is all blurred together. So I picked purple. I know. You're like, what? Yeah, factor loadings are fixed effects, but they belong to the model for the variance. Stay tuned. Anywho, we're talking about missing predictors at level 2 first off here. So I have some bad news for you with respect to how multi-level models handle missing data. They don't. It's a common misconception. And in longitudinal studies, there's a lot of reasons why we might have missing data. Sparse missingness, so when people just don't come back or they don't answer certain questions, do certain tasks. When they deliberately don't come back, so attrition or dropout as you would call it. You can think of unbalanced time as a kind of missing data, like if they were supposed to come at time 3, but they came at time 3.2 instead, then the time 3 observation that you had intended for them is missing. Planned missing data is a thing. You can deliberately decide to only give certain people only some outcomes. And if you make sure that there's balance so that every pair of outcomes is observed enough times, you can stitch it all back together again in an analysis. However, I just tried to do something like this with items that went so badly that M+ wouldn't converge because it was below the missing data tolerance. So be very careful if you're going to use a planned missingness design. And the other piece of it that I think is often unrecognized because it's implicit is there's selection bias at the beginning of research studies as well. So this is very prominent to me coming from the world of cognitive aging. If you think about studies that sample older adults, do you think the people who start the study at, say, age 65 are a random subsample of all the people who could have become 65? No, decidedly not. And as you study people as they get older and older, they're increasingly more selected for what I would call the super seniors. The ones that are still have enough cognitive and physical functional abilities to go participate in research in the car and drive themselves there, or to figure out a bus schedule and get there, like however it works. So a lot of times I've seen criticisms of longitudinal research in the context of cognitive aging, because it's like, oh, well, you have all this attrition and then it's biased and it's wrong. It's like, no, the attrition was there in the first place. It just gets worse as time goes on. And I've actually seen results where it looks like as people age, on average, there's a growth trajectory instead of decline. Because of the way that the bottom drops out of the study, then it looks like who's left is actually growing. So missing data does happen during research, but it happens before the research starts as well, just to be aware of that. In addressing the contribution of missing data, the goal is to try to get the right answers back. The goal is to try to make valid inferences despite the missing data. The goal is not to fill in the missing values. Any techniques that do so are not really trying to fill in the missingness. They're trying to make sure that the missingness doesn't bias the conclusions that we draw. And what's often unrecognized is that all of these missing data methods have distributional assumptions baked into them. So you still have to pay attention to that aspect of what kind of value you would be dealing with. So things not to do, ever, single mean replacement or regression imputation. This is like an option in SPSS. I'm assuming it's an option in other packages as well. But you can say, hey, can you just take this column of missing outcomes and just fill in the mean? Or you can say, hey, fill in the predicted mean from this set of predictors and just fill it in straight away. Now, why do you think that might be a problem? There's no error? Yeah, you're filling in the prediction. Like it's going to be right on the line. It's like it's artificially so. So the idea then is to try to fill in things potentially if you're going to go that route, but add error to it. So that's where we have options. And if I haven't already shouted out this course, Missing Data course next semester being offered. FIML, as it is pronounced, is one way that people address missing data. Full information maximum likelihood. That's what we've been doing the whole semester, by the way. That's not different. We've been doing FREML, which is not an acronym, but I'm trying to make it one. So residual maximum likelihood is full information. That term just means that you use all of the original data in estimating the model parameters, rather than summarizing the data into some kind of covariance matrix first. Asymptotically equivalent results will be obtained through multiple imputation and full information maximum likelihood if you use the same variables in your imputation model. So briefly though, what full information is you remember how I just said, don't fill in the mean, that's bad. Okay, scratch that. We're gonna fill in the mean, we're gonna add an error term to it, and then we're gonna do that like 37 times. And then we're gonna repeat our analysis across each of the 37 data sets and concatenate all the results together using special formulas that pay attention to the variability across the data sets and within a data set. That's called multiple imputation. Now, critically, you cannot just average the data sets back together. I once attended a conference presentation where someone put forth this idea, and the people in the audience were like, you can't do that. Like, it wasn't even, oh, that's an interesting idea. I wonder if you've ever thought about, no, you can't do that. Because what happens if you average out errors? Like, right back to the line again. So it's not different. So we don't want to average data sets. You would average the results from separate analyses on each of the data sets. That's multiple imputation. I think Bayesian approaches in which you try to go back and forth and filling in the values and estimating the model are probably more realistic. And that's something that I would personally like to learn more about than what I know. My point in telling you this, though, is that both of these things assume missing at random. So with respect to missing data, there's a taxonomy that pretty much everyone uses, and there are 3 major categories. So if you have missing predictors, then your choices are missing completely at random, missing at random, or missing not at random. Completely at random is what it sounds like. There's absolutely no reason that the variable does not have that information. So for instance, if you were handing out questionnaires and you discovered too late that the copy machine ate page 5 for some people, and so they couldn't answer those questions, like there's nothing about what they would have said that caused the copy machine to decide to eat their page. So that's completely at random. Planned missingness, where you randomly assign people to only answer some questions or do some tasks, would fall under that category. Missing at random, however, is what all of the missing data methods assume, and they have to assume it because it's not testable by definition. You are lacking the data it takes to test it. So there are tests of missingness that you may have come across, like in SPSS, I know there is one. That's an MCAR test, because what they do is essentially decide, is there any variable in your data set that predicts the probability of missingness? And if there is, it's not completely random. It has to be some other kind. Missing at random means after controlling for the information you do have from a person, then it's conditionally random. Like you have enough data, for instance, to draw the shape of their trajectory correctly, and the points that you're missing would not have changed what that looks like. Or you have enough people who have similar profiles on your predictors that you could make a reasonable inference as to like how they would have done based on all of those things too. So this is a favorite comment from reviewer 2 or 3, whichever one you decide to dislike the most. It's always reviewer 3 for me, but now it's reviewer 2. Because missing at random is not testable, reviewers always want you to test it. It's like, well, now what? all you can do is try to make an argument that your model contains information that would be relevant to the missingness. I think that's the best you can do. And there are ways to introduce information not as predictors, but just as part of the missingness aspect called auxiliary variables. I cannot say that word to save my life, or spell it. Auxiliary. How's that? Auxiliary? Judge's ruling? No, it's not ancillary, it's,
Just
there's an
auxiliary.
X.
Auxiliary?
Auxiliary. Auxiliary. Okay, judge's ruling. We got that. So look for that as a keyword for those types of software options. Missing not at random is the bad one. That means missing this for reasons and you don't know what they are. So in these families of models, usually what you would have to do is deliberately introduce some way of make caveating, is that a word? Like conditioning your results on this assumption, like, well, if missingness were because of this, then here's what would happen. Those are called selection models, among other things. And there's no way out of this. And this is probably the most likely, but we just pretend it's not, because otherwise we can't do anything.
Or we just have to put it in the limitation section of the paper.
Yep. I think missing data is always a fair limitation to talk about. And you can say you did the best you can, but there's no way to know what you don't know. So the bad news is that maximum likelihood with respect to multi-level models does not fix this. And this is more of a software thing than a modeling thing. The rule is all rows that are complete get included in your model. There's no addressing of missing data other than that. So while most multi-level modeling programs, so we're talking Elmer, mixed, those kinds of things, do not require leastwise deletion of whole persons, you can use whatever complete occasions you have from them. The question then is, which occasions are complete? Now, we haven't talked to this up to this point, because if you have an outcome, odds are good you know when it occurred. So like the time variable is not likely to be missing if the outcome is there. You know when you got your data. Especially nowadays when computers will log times and dates and things without you even having to do anything about that. The predictors, though, may not be the case. We could have missing predictors that are people things or time-varying things, and that means that your sample size may change across models. So if you're not going to do anything extra with respect to your missing data, this constraint means that you'll need to pre-select your sample as to include all the cases that you would eventually want to include. Otherwise, the -2 log likelihood, AIC and BIC, are only comparable from the exact same sample. Like they're literally the sum across observations, and if it's not the same set of observations, the sums are on different scales. So there was, I used to give essay type homework things in these sorts of classes, and one of my favorite questions that usually stumped folks was this. Let's say that you're estimating a model, and you add a new predictor, it's maximum likelihood estimation, and your predictor is not significant. But your log likelihood improved by like 200. How can that be? How can you have a non-significant predictor according to its Wald test p-value that nevertheless, if you were to do a likelihood ratio test, results in a significant improvement?
So it dropped people?
Dropped people, that's it. Fewer people means smaller. It's just math. So Jonathan told me a story about being at a conference once where someone was looking at doing replication kinds of analyses on different samples, and they fit the same model on 3 different data sets. And then they said, well, the AIC in this data set is the lowest, so it fits best in this one. Nope. Data sets are on different sized people. They're not comparable. So you would want to control for potential missingness if you're not going to do anything about it by booting cases. And that is not a great idea. Anytime you remove cases that are incomplete, you'll have less power, and you're potentially limiting your conclusions to the people who are complete, like the people who made it all the way through the training program or all the way through whatever you're doing. So to put this into a little more concrete terms, if we start out with a wide data set like this, so this is what you would need to do traditional repeated measures analysis of variance. This is also what you would need to fit longitudinal models using structural equation modeling software, where each of these T1, T2, T3 things would be separate boxes that you would then have latent variables predicting. So let's say that we have an outcome measured for 4 occasions. I have a person level predictor that was measured once, and then I have a time varying predictor that was measured 4 times as well. I can restructure this wide data set into this long version, and it is 1 row per occasion per person. So that means I have a person ID that's pasted down. I have a time ID that would be stolen from the names of these columns, or otherwise you would have to have exact observations as to when they were. Dependent variable here was observed for the first person all the times, but their time varying predictor was only observed for the first time. And the second person has even more missing data. So if we look at this table right here on the left, and riddle me this, which rows would be included if the model was unconditional and had only time predicting the outcome? Oh, we got 1. Is that in or out?
Can you say the question again? I'm sorry.
The question is, if I fit a model that has just time predicting an outcome variable, so the unconditional models we've been working with up to this point, which of these rows gets included? So first one, second one, third one,
Or
Fourth
1
one.
and 3.
yeah, so the only one that wouldn't would be this one right here. 1 to 6 and 8, no problem. Now what if we add a time varying predictor, which we're not going to do this semester, but maybe next semester? This column right here. Well, we get 1 to 3, not 4. We can have 5, not 6, and 7 and 8. Now what if we add the person predictor that was measured once? Question?
Would we have 7 in that one?
7 would not be there because there's no outcome.
I heard that might have just been me. I thought you said 7.
I may have said 7, and if I did, I screwed it up.
Okay, I'm sorry.
See, this is the part I don't go back and edit the transcripts, right? The class is an honest rendering of all my screw-ups, for better or worse, so thank you. So 1 to 3, 5 and 8. What if I add the person predictor? Bad news. 1 to 4. If this person is missing whatever covariate they collected at baseline, they're missing it all the time. Bye-bye. Listwise deletion of whole people. And what if I have everything in? 1 to 3. So you can see where this gets ugly real quick. When you have lots of variables with different patterns of missingness and your sample gets down to not that much. So MLM doesn't handle missing predictors. The only way to handle missing predictors is to bring them into the likelihood. So I once emailed Craig Enders about this when I was first putting this together, and I was like, how would you talk about missing predictors that are time varying? Because I think we can all agree that missing invariance predictors, so like this one here, leads to MCAR, because this person would not be in the analysis at all. But it's kind of ambiguous, and so his answer was somewhere between MCAR and MAR for time varying predictors. Because you do have some of them for somebody potentially. It's not like the whole person leaves, but the occasions where they didn't answer that question are gone. So it's somewhere in the middle is what he said. I thought that sounded like a reasonable compromise. Okay, how are we doing so far? Have I bummed you out? No? Takes more than that, a little bit? What can we do instead? Bring the predictor into the likelihood. So this is where multi-level modeling within SEM software shines. Because the problem is that in mixed, there's only one outcome, right? There's one column for Y. You're locked into that. And so therefore the likelihood is all about the means and variances and covariances of Y that are being recreated by your model. In multivariate software, so that's the transition to SEM software, you can predict multiple outcomes at the same time. So essentially what you can do is tell your program, hey, you know that predictor that I have? Can you pretend it's an outcome? And it's like, sure, how would you like me to do that? Well, I'd like you to estimate its mean and variance. You essentially fit an empty model to predict your predictor. And that renders it as an outcome, even if it's not being predicted by anything. So that's where the language gets a little tricky. because it's a predictor in the way you're thinking about it, but it's an outcome in the way that the program is thinking about it. If you do that, then the rule is that you don't have to have that missing cases will not get dropped out. Like you can keep whichever ones are there. It's a joint likelihood instead of a conditional likelihood, if that means anything to you. Doesn't mean a lot to me, but I know the words, so. Those are words they say over in stat, right? Or in other classes? Yeah. So if it's an outcome, that means that we have distributional assumptions. So you got to be willing to believe them or find software that allows you to have the appropriate link functions and conditional distributions to go other ways. And that depends entirely on the software. So that's often unrecognized that you are making distributional assumptions when you do this trick. The other one is multiple imputation, which I described earlier. You fill in the missing values, you add error to it, you repeat the analysis on each of the imputed data sets. It's analogous to the use of plausible values within some large educational data sets, like NAEP, I think, does this, maybe PISA. Anyone else know? I know NAEP for sure because there's like a training on how to do it. So in NAEP data, it's NAEP, and I don't know what that stands for. They end up with 5 different plausible values of each measure that they took. These are factor scores, essentially, and they give 5 per person. And so you're supposed to run your analysis on all 5 and then put it all back together again. So this does show up in other contexts besides missing data, because you can think of factor scores as missing data. They're latent, right? They don't exist. So it's kind of a missing data problem. So what we're going to do in this class the rest of the semester is this. La, 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 it's missing at random. I don't care, don't tell me that. That's what we're going to do. But just know that that's not the best strategy. Luckily, in most of the data sets I've worked with, I had reasonably complete data where it wasn't going to be a huge tragedy if I had to delete a few folks here or there, but I can see where this would go sideways very quickly. All right, questions or comments on any of that? We're not bummed out, though. We're good. Vladimir, go for it.
Yes, Lisa. So if we have our predictors in the joint likelihood in the model, the missing data will be predicted in some way plus some error, and that will be used as input.
It's not being filled in, but you are essentially trying to find the mean, variance, and any covariances involving that predictor that's in the likelihood as if it were an outcome.
Got it. Okay, thank you.
Yeah. In the univariate approach, then you have to have all the predictors be observed. Otherwise, you can't build a y-hat. If you can't build a y-hat, you can't build your residuals, and then you can't get your variances. So, like, that's the problem.
Great, thank you.
Sure. So time invariant predictors, synonyms for this, level 2 in this context. People things. They are things that you care about or things that you control for. So you can think of this as more substantive predictors, control variables, or also predictors of missingness. Anything you know about a person, like did they change schools? Did they drop out of schools? Any other reason you can think of that they didn't come back would go into this. And it can be things that do not change over time. So like the sex you were assigned at birth, for instance, is something that can't change over time. But if you wanted to go more psychological than that, like gender identity, certainly can change over time. So that would not be a good example. It can be things that are not likely to change, but you might have to argue for this. So if you collect education levels in a study of working adults, there's not a lot of folks who would necessarily go back to school and change their education, but there are certainly some. And it can be things that do change across the study, but you've only measured it once. So then that's a potential limitation. For example, if I'm measuring children, let's say 10 to 18 on something, and I ask the parents a bunch of questions about their parenting style when the child is 10, but I don't do it again throughout the time. If I have a variable that I'm thinking of as parenting strategy, that's not a good enough label. It's parenting strategy at age 10. Because undoubtedly, strategies are going to change over time, and if you haven't measured it, you can't talk about it that way. The same thing happens for any kind of person predictor that is perfectly correlated with time within persons. So we talked about this a little bit last time in terms of what the metric of time would be. So if you have a study in which You have third, fourth, and fifth graders, and you measure them repeatedly over time. Then within persons, like it is 1 year later, but you're also 1 grade higher. Grade and time are the same thing within persons. So to break that tie, if you wanted to control for their graded entry, you would treat that as the time invariant predictor. Whether you started at third, fourth, or fifth is then a characteristic about you that would potentially moderate your trajectory, the same as anything else. So stuff that you've measured once is the idea here. It could be something that changes, in which case you have to argue why it made sense to only measure it once. Centering, we're going to do that still. That should surprise no one in this room. So we want to center all predictors so that 0 is a meaningful value. And this will change the definition of the intercept. It will also change any main effects that are part of higher order interactions, because they are conditional on interacting predictors being 0. So 0 needs to mean something. For continuous predictors, quantitative variables, people commonly center at the mean. That's fine. There's nothing wrong with that. But I would also say any other value that's meaningful is a good choice. So the minimum level of something, because we're always talking about what happens as x goes up. Well, then x can only go up in that situation if you center at the minimum. A meaningful point. So in my examples here, I have education as a variable that I usually center at 12 years, which would be consistent with the reference person having a high school degree. If I chose the mean, though, like in one data set, the mean years of education could be something like 14.67. But there's no single person who wrote that down, I can guarantee it. And also, mean education doesn't really describe the sample very well. In some samples, the mean education might be 8th grade. In other samples, like the older adults that I tested as part of my dissertation, who are all retired faculty and their spouses, the mean level of education was a master's degree. So I centered at the mean doesn't help you describe like who your reference is, and it doesn't help it translate across samples of different kinds. So I would pick the mean if it's an arbitrary variable and no one cares what the numbers are anyway. I would pick some kind of meaningful reference point if you have it. It's easier to think about than representative people that way. For categorical variables, somebody's got to be the 0. You can set them up in multiple ways. I don't like effects coding for those. So that's the -1, 1 combinations, where the mean then is 0, because the mean is like, who is at the mean of a categorical variable? Like a 0.5 is weird to me, but it's a choice. 0 means something, that's the idea. Here's a couple examples from the other class, crossover event, on how to set up different coding schemes for categorical predictors. So this is, on the left here, is an example of what is called indicator coding, at least in the textbook I use for regression. And the key idea here is that you would set up one group as the reference, and so then that group would have their mean be the intercept. So I've got the columns of ones in here as a reference for all the fixed effects. You would then turn on the value for one of the groups, only one at a time. So then when all is said and done, the first slope here would give us the difference between A and B, because we have A and C lumped together with the 0, and then the second slope would pull them back apart, and then that would give us the difference between A and C. And you could still get the difference between B and C as a linear combination. That's one way to do it. Another way to do it is called sequential coding, or what you might call in this class a piecewise model. That's another way to think about it. It's the same idea. And this one is for ordinal variables, such as an ordinal rating of happiness from 1 to 5. In that case, I set it up so that the first answer, a happiness level of 1, is my reference. My first slope would then cover the change from 1 to 2, and then it shuts off at a 1. The second one starts off at a 0, picks up where that one left off, and covers the change from 2 to 3, and then shuts off at a 1, and so on. So then this gives you like a little stair step. Like, what's the difference between 1 and 2, 2 and 3, 3 and 4, 4 and 5? And for ordinal data, I think that makes probably more sense in a lot of cases. Then any of the other differences, like if you wanted to compare 1 and 5, for instance, that's a linear combination of the other slopes. So it's up to you how you set it up. There's a lot of choices on this, though, that might be reasonable. So what do time invariant predictors do? The good news is that there's relatively few things. So if I have a model of within-person change, that means I'm fitting some kind of like growth curve analysis. Well, they can adjust the y-intercept and not the slope. So for instance, this picture would be consistent with an X level 2 predictor. Let's say that there's a high group and a low group on this for convenience sake. And if the darker line is higher on X, that means they start out higher, but they don't change differently. So a main effect of a time invariant predictor is adjusting the intercept specifically. If you add in an interaction with time, then the role of that interaction term is to change the time slope. So high people grow more than low people on X. Now the rest of this, I have main effect of X question mark. Why do you think I have a question mark? Zoomers are quiet today. I'm watching the chat still. Don't talk to me. What would the main effect of X, like how would I decide whether I would have likely to have a significant main effect of X, for instance, according to this picture?
Would that be non-parallel change?
It is non-parallel change. So what would dictate whether my main effect of X is likely to be significant or not? Where are group differences being evaluated? I'm seeing gestures, but I don't know what they mean.
At 0
At 0 of what?
times
At
0?
time, yeah, because if I have X times time, the time slope is conditional on X of 0, the X slope is conditional on time 0. So in order to know what to expect with respect to a main effect of X, I got to know where time 0 is. If I put time 0 at the beginning here, then there may not be a main effect of X. But if time 0 is at the end, there may be. That's up to you. Likewise, the main effect of time would be specific to the 0 value of X. And then the interaction term says what happens to it after that point. So you can think of an interaction of X by time here as doing two things at once, the same as any two-way interaction. The easiest way to think about it is that X is going to control the time slope. It's going to moderate the time slope. The other way to think about it is that time moderates the effect of X. So X shows up more at the end of the study in this picture than at the beginning. There's a bigger difference. And you can have stuff that looks like this where there's both. There may be intercept differences at time 0, and those differences may grow over time via an X by time interaction. And each term that creates your growth trajectory could potentially interact with X. So X could make the line differentially bendy. Or each slope can have an interaction with X. Do you think you can have more than one X? Sure we can. Can have lots of letters. X1, X2, all the fun stuff. In a within-person fluctuation level, there's not a lot it can do. So if you don't have change, then these are your choices. Main effect of X shifts the intercept or not. There's no trajectory with respect to time for it to do anything with. So this one's a little more straightforward. However, I want to put a pin in something else that exists that we may get to in the advanced class, but maybe not. I didn't get there last time. We'll have to see. Location scale models. So these were, I believe, invented by Don Hedeker, one of my idols, and he's written software packages specifically to estimate them. The idea is that you can have effects of time invariant predictors in the model for the variance as a way to introduce heterogeneity of variance. So, as an example, let's say that I have treatment versus control, simplest case. In addition to treatment versus control adjusting the fixed intercept or adjusting the time slope, lots of gestures for these ones. It can also be related to the amount of variability. So maybe after treatment, people in that condition are more variable relative to each other than people in the control condition. That could be a thing, and actually is a thing. Differential response to treatment would create differential heterogeneity of variance. So at level 2, you could introduce separate G matrices by group. Likelihood ratio test to see if that makes the model happier. That is directly analogous to a multiple group model in a structural equation modeling context. It's the same idea. You can do it in mixed effects models as well. You can also have this for quantitative level 2 predictors, but finding software to do that is a little trickier, because then you'd have to have the G matrix change in a continuous fashion as a function of some other thing. At level 1, you can also have the amount of within-person residual variation differ as a function of person-level information. So if you think of this in terms of fluctuation, this has to be a gesture thing, right? Let's say that I ask for stress every day for a month. You get this, right? Some people are like this. Some people are like this. So you can actually have another kind of random intercept that controls the size of the residual variance across people. It's called a random scale factor. I know that's like, what? But think of it in that context. If you think of the idea of a personality trait of inconsistency, like some people are moodier than other people. Not grumpier, but moodier, right? They're more volatile. Some people are more consistent in their health behaviors. Some people get up and eat a nutritious breakfast every day and get their, hour of steps in, and the rest of us are pounding Halloween candy at our desk, hypothetically speaking. Not me, because only licorice is left.
This is called a latent scale factor?
So the idea of a random intercept that controls the differences between this and this in terms of your amount of residual variance is called a random scale factor. And I put a link to something here. I wonder what it is. Let's find out. I don't remember. It's going to be a surprise. Oh, it's a picture. It's a video.
Hi, well, hello.
Hi,
I'd
Don.
like to introduce.
That's what it is. It's a YouTube video that Don made about these models. So, there. You don't have to listen to me. You can listen to him. In models of change, though, this makes a little bit less sense, because if you have a growth trajectory, the e's around it are tracking the fit of the line as well as the extent of unexpected fluctuation. So then it's a little more ambiguous as to how you would think about that. But in these models, the default assumption is that residual variance is the same for everybody. That people are equally variable, and that is not only a testable assumption, it's unrealistic in a lot of contexts. Extending this to clustered data, I don't want to confuse folks, but just to put the idea out there, in clustered data, we would have people nested within groups of some kind, like people who work for the same company, and you'd have multiple companies. These models get used in that context to index relative disagreement. Like, how much do you like your supervisor? And there are some supervisors where everyone's going to be like, meh, and there's others where people will love them and hate them and average out to meh. Now, is that the same person? Probably not. In the context of a classroom, course evaluations, right? You can have polarizing people that ends up in meh on average, or you can have a straight meh average because you're just straight meh. So that would be indexed by differential residual variance across clusters, across bosses or supervisors in that context. In a longitudinal context, it's within person inconsistency is what residual variance is tracking, and you can have individual differences in that. So, and me and my former student wrote a tutorial a couple of years ago, a review paper in which we talked about this for the whole second half, because Ryan Walters wrote his whole dissertation about that. So there's that for you as well. I know how to do this in SAS NL Mixed. I have not played around with it in R yet. I'm sure there are many R packages for it. In M+, there is now an option called log_v in the multi-level SEM part of it that allows you to introduce this, and then it creates a latent variable in the between model that you can then go and do stuff with. So I think these are super cool. They kind of hurt my head a little bit, but I just want you to know about them, because if you have hypotheses about variability, this would be the way to do it. So, does that make anyone excited? You're like, if I nod, will you stop talking about it? Can I tell you a very brief story about these models? So where I stumbled into this was during my postdoc. I had, so my advisor often gave me opportunities to help analyze other people's data, which means he didn't want to do it. And he's like, here, you can learn on this data set and I'll help you with it. I'm like, okay. And so we had someone who was examining older adults in a nursing home, and they were looking at how reliably they could trust the patients to index their own mood, because they were trying to do some kind of intervention that made them happier and more consistently happy, because folks who are in that situation often are somewhat volatile. And then as sort of a pilot part of that, they had to figure out, how do I reliably gauge mood? Because you can ask the caretakers, how grumpy do you think Mrs. Smith is today? Or you can try to ask Mrs. Smith directly, who may or may not have the wherewithal to answer you. And so what she was focused on, though, was not just improving their quality of life, but the consistency with which they experienced quality of life. And so she wanted to see if there were differences in variance, is the question. And I was like, well, I don't know how to do that, but that seems like a thing that should be possible on Earth. So I start going through all the books that I had and all the books my postdoc mentor had, and I found in the SAS Mixed Models book that Walt Stroop and several other people authored, it was like made by the SAS people, Chapter 8 had this little section on heterogeneity of variance, and in the repeated line, you could put in a linear predictor that allows for differences in residual variance. And I was like, excellent! So I did this whole little thing where I showed that mini mental status exam, which is a crappy measure of cognitive functioning in older adults, that people who were worse on that were more inconsistent over time, and people who were better on it were more consistent. And I was like, okay, we have a signal here we can detect. And the methodology for that was sufficiently complex that the Journal of Gerontology, whatever, I forget where it was published, was not here for that. So I ended up writing a separate paper just to describe the models, and I submitted that to MBR. And so then I said in the gerontology paper, go see this for how I set up the models. So it was like a crossover event. Well, the MBR folks, I made this little paper, and they're like, you need to make this a tutorial. Make it longer. Add this, add this, add this. And I was like, okay, I'll make a tutorial. And lo and behold, that paper co-won the journal article of the year for that journal. And I was all proud of myself. No applause yet. So come to find out, after learning more about these models, that I did not have a random scale factor in the model because it wasn't part of the SAS Mixed Models book, Chapter 8, what I was going from. And I was testing time invariant predictors of variance without the equivalent of a random intercept. So essentially, on the variance side, I was treating it analogously to a linear regression where there was only one pile of variance and there should have been two. So I have not gone back to prove it to myself, but I'm about 95% certain that my award-winning paper is wrong. Completely wrong.
Thank you for your honesty. Yeah, that's science.
Yay, science. Yeah. But I'm keeping the trophy. I am keeping that asterisk on my CV. You're not going to take that away from me. But the funny part is when I get asked to review papers that have cited that paper. And the review, and they'll say things like, Hoffman developed this method, and it's like, well, first of all, no, I didn't. It was a tutorial on the SAS book, and second of all, don't trust Hoffman. She doesn't know what the fuck she's talking about. Like, no. Do better than that. So, I have a long history of being interested in these models. I think they're super cool and super useful. They are an order of complexity higher than what we're doing, but I just want to put it out there that they're out there. End of story. Maybe the punchline to that story is, just because it's published doesn't make it right. We all need to be our own peer reviewers, and just because it's published in a good journal doesn't make it right either. So one thing that you can't really do, and Vladimir, I need you to cover your ears for this because it's going to hurt your brain. This is all what his thesis is about. You cannot have random slopes of level 2 predictors in a 2-level model. Here's the difference. If I have an x-axis of time, I can have a pink person have 4 occasions and a blue person have 4 occasions, and I can draw them their own lines through their 4 occasions, and that's totes fine. And then I can estimate a variance as to how different these slopes are across people, and I can predict why that is. What makes the pink person different from the blue person? I don't know, let's find out. But if I make the x-axis group, like whether they were assigned to a control group or a treatment group in a between subjects design, then at each occasion, they're in the same group. So I've got 4 blue points stacked on top of each other and pink 4 points stacked on top of each other, and I can't draw a line through a dot. So there's no such thing as a random slope for a level 2 predictor in a 2-level model. However, some folks have put them in anyway as a backdoor to introduce heterogeneity of variance. So it's kind of like the location scale models, but it's done through a different mechanism. But I would tell you for now, it doesn't make sense conceptually to think about random slopes for level 2 predictors in the same way that we're thinking about them for level 1 predictors. Okay? Did I do okay? He's like, no. All right. So what would this look like? Let's go back to straight up unconditional models. So random quadratic being one of the more complex ones that we've seen thus far. This could be log time or regular time. You take your pick. So time is going to be session minus 1 here. So this is long stacked data. That means I would have an individual intercept, which is composed as a fixed intercept plus intercept deviation. I can have a linear time slope. That's going to be conditional on time 0 and have its own deviation. And if there is a random quadratic, the random linear slope is also conditional on time 0. And then we have our quadratic that has the fixed part and the random part, and it takes at least 4 occasions to fit this model. Okay, now note the subscripts. The first subscript keeps track of which beta the fixed effect goes with. That's why this is 0, this is 1, and this is 2, because it matches the betas. The second subscript is 0, because this is a counter as to how many fixed effects we have in that level 2 equation. I'm going to use the term starting point. So gamma 0, 0 is the starting point for how people get their own intercept at time 0. Gamma 1, 0 is the starting point for how people get their own linear time slope at time 0. And then gamma 2, 0 is the starting point for the quadratic slope. Now what if we add something like education? Let's say that we have years of education, so it's a quantitative predictor. Then if I put in a main effect, its job is to adjust the intercept. So I would have the difference in expected outcome at time 0 per year of education is what that slope would give me. I can also have an effect of education on the linear time slope. That is actually a 2-way interaction. So that's what the pictures were showing earlier. That moderates the time slope, so that fixed effect would tell me the difference in the expected linear rate of change, not the intercept, the rate of change per year of education. And I can do the same thing with the quadratic slope. That fixed effect would tell me half, the difference in half the rate of acceleration or deceleration per unit education. So in this model, how many kinds of individual differences are there? On slide 15 here. How many kinds of individual differences? How many blue things in level 2? Yeah, 3. People differ in their time 0 expected values. People differ in their linear time slopes at time 0. And people differ in their quadratic time slopes. That means 3 ways people differ from each other. Education can do 3 things. So let's introduce it then. First off, education here, let's say that it's centered such that 12 years is the 0 point. And education only gets an I subscript. Why do we think that might be?
Because it doesn't vary over time.
It doesn't vary over time. Likewise, anything in these level 2 equations only has an I. There's no T's up in here. Down in here? I don't know. Well, it's under it, but it's level 2, so I'm not sure which metaphor to go with. Up in here. I'm going to go with up in here. Note in level 1, YTI, time TI, ETI. In the notation, if you put a variable in the level 1 model and E counts as a variable, it's TI. So let's go through one by one here. Beta 0 I is still how each person gets their own intercept. Now it's doubly conditional though. It is conditional on time 0 because of the level 1 model. It is conditional on education being 0 because of this. So now the fixed intercept is specific to both 0 values. And I know this looks complex, but this is not a different concept than you first learned in regression. The intercept is conditional on all predictors being 0. We've just added education and time. Now gamma O1, we have a 1 in the second subscript because this is the first predictor of beta 0 after the starting point. So gamma O1 is the change in the intercept specifically per unit change in education. So people who have more education could start out higher on this outcome, or they could start out lower. And then U0 is still the idea of an individual deviation, but now it's deviating from something different. It's deviating from the intercept at time 0 as predicted by a linear effective education. So anybody who graduated from high school, 12 years, would have the same predicted intercept. U0 is then how far away from that. Anybody who went to 14th grade, same intercept. U0 is how far away from that. So U0 now, we're still going to call this the random intercept, but some textbooks will switch terminology to start calling these level 2 residuals because they're left over. This is the U0 that's left over after controlling for education. I'm not going to do that to you. These are going to be leftover random intercepts. Deal? I'm not going to adjust the terminology. I think that's too hard. So that means that if I put in education, I should be explaining some of this U0 variance, and I should be able to compute a pseudo R-square for it to see how much of the intercept variance was due to education, and then see how much is left over. Okay, with me so far? Ish? Hey, this is what I'm hoping for. If I get anything above flat, I'm doing good. Horizontal, not vertical. This is vertical, this is horizontal. Got it. I have to remember this because I say I'm vertically challenged. That means I'm short, and that means this is vertical and this is horizontal. Mnemonics, they help. Beta 1 then. Same ideas. This is how each person gets their own linear time slope. The jumping off point for it is now also doubly conditional. Because this is a linear time slope in a model that has a quadratic time slope, this time slope is at time 0. And because education is in this beta equation, the jumping off point, gamma 1O, is conditional on education being 0 too. Now what this is the main effect of time. That's what gamma 1O represents in this notation scheme. That means gamma 1,1 is education by time. Yes, thank you. Not proud of the fact that the people in the hallway can talk louder than I can, but I'm trying to do the best I can. So this is an interaction term, right here. It doesn't look like it because it's just sitting all by itself, but if you dump everything back into beta 1 and then take it back up here and multiply it by time, then you distribute it, it's education by time. So education by time says how the linear time slope changes per year of education, specifically. Not Y, the linear time slope. Two-way interactions adjust their main effects. Main effects adjust Y as a concept. So ed by time either says the time slopes depend on your education, or the effect of education depends on what time it is. Take your pick. U1 then is still the deviation of each person's linear time slope from the one that's predicted, but the one that's predicted is now based on education. So we can compute another pseudo R-square for how much of the variance in the linear slopes was due to education and how much is left over. Now, up to this point, I want to make one statement that may confuse you, or it may help if you use HLM software. Has anyone seen this program before or worked with someone? You have? So their output is organized in a way that is a little painful. But from this perspective, they would call this term right here, gamma 0, 0. This is the intercept of the intercept. Gamma 01 is the slope for the intercept, because this is the slope of education predicting the intercept. Gamma 10 is the intercept of the slope, and then 11 is the slope of the slope. Like, that's how the output is organized, and you will see tables organized with those headers. And if you're like, how the hell is this the slope of the intercept and the intercept of the slope, and those are not the same thing? They're not the same thing. It's that one or that one. I don't enjoy that notation, but it exists. So I go with starting point, and then each of these things modifies that starting point. But this is the main effect of intercept. This is the main effect of linear time. That means gamma 20 is the main effect of quadratic time. And guess what gamma 21 is here? Yeah, I'm putting my mouse in front of it to block it from you.
The difference in quadratic slope for each change in year of education.
Yeah, it's the difference in the quadratic time slope per year of education, otherwise known as a three-way interaction.
Oh, because times squared.
Times squared, yep. I tried to warn you. Now, how many variables are in this model at this point as predictors?
In the model for means?
In the whole model, how many predictor variables do we have? Two. Time, education. How many parameters do I have? And don't say 37, because that's my number for things that are a lot. It's not quite that bad. Let's count them up. How many fixed effects?
6.
6. How many red things, essentially, right? How many blue things?
4.
4. How many covariances among the blue things?
6.
Not in, 6 things in total in the G matrix, but how many covariances specifically?
3.
3. So altogether, 13 parameters. And I got 2 predictors. Do any of you who do longitudinal research only have 2 variables in your data set? Nope. So you get a sense as how exponentially complex this gets real quick. But if your unconditional model of time is this random quadratic, let me back up, if this is what you're at, like what you have found out is that people differ from each other in 3 ways. And so each of your person level variables has the chance to contribute in 3 ways. Okay, so the composite equation looks like this then. If I shorten everything up, here is the level 2, level 1 version. If I distribute and then don't use the betas, this is what it looks like instead. So then I think the composite equation makes it easier to see that gamma 11 is ed by time and gamma 21 is ed by time squared. So what if I added a second time invariant predictor and I added its main effect? What subscript would it get right here? It would get an I, but the fixed effect for it. Let's add another person thing. I don't know whether you have blue eyes or brown eyes or hazel eyes or green eyes. How's that? What would its subscripts be for its fixed effects? I got 01 for the first one, 02, and after that? 04, 05, yep. So the number in the second spot would index which term you're on in beta 0. What if I added my second predictor here to the beta 1 equation? What would its subscripts for its fixed effect speed?
1, 2,
Yep, 1, 2, 1, 3, 1, 4. And down here,
2, 2.
yeah, 2, 1, 2, 2, 2, 3, and so on. So it's like a grid, kind of. If you see subscripts that are both numbers, that's some kind of interaction term. If you see a subscript that only has 1 0 and 1 number, that's some kind of main effect. It's not exactly row column, but it's close enough for my purposes.
Quick question.
Yes.
Can we have interaction within level 2?
An interaction within level 2?
Yeah.
Yeah, like does the effective education depend on your eye color or something?
Yeah.
In my stupid example?
Yeah.
Sure you can. So now we've got education, eye color, education by eye color. What if you have a third one? You want to throw a 3-way interaction in there? Sure. Education by eye color by hair color. Sure. And then we put it in here, and you know what that is? That's a 5-way interaction. Would not recommend. Question from the Zoomers. So if there are 13 parameters, does that mean we would need more than that number of occasions? No. This model would still be estimable with 4 at a minimum. 4 would not usually be enough to get a good random quadratic estimate, though, but it's technically possible. The number of level 2 predictors that you can have is dependent on the number of people you have. You're going to run out of degrees of freedom otherwise. So if I have 50 people, I can have 49 level 2 predictors, give or take. Now note that this is a linear effective education. Could education have a bendy effect instead? Could I put in education squared to make it bendy? Yeah. So this is actually a simplification in that regard. We are assuming education has a linear slope for each of these things. And you're like, please stop talking. It hurts. It does hurt. The good news is that it's not difficult, it's complex. Like these are all concepts and words that you already have. It's just you're putting them all together at the same time. And that's the hard part. But we'll do examples and it will get better. All right, 143. Any questions as we wrap up for the week? Zoomers are good? All right, then let us know if you need anything with respect to homework. That's due Monday, and I'll let you know when you have something else to do. Thanks for being here. Have good weekends. Hang in there. Way to conquer week 12.